a motivational lecture in the previous session. Today I will like to start a discussion of energy and thermodynamics, but with an atomistic view. So I will not be talking mostly about gases and pistons and engines. Rather, I will approach the subject from the point of view of modern physics. So in physics, most of the things that we deal with, they are modeled mathematically. So we have a model, and a model is simply some kind of equation that describes the behavior of the object. For example, we can have an equation of this form, where m is a constant, k is a constant, x is some variable, a function of time, and this is the double derivative of x with respect to time. So this is an equation. It's called a differential equation, and in our recitation sessions next week we'll learn how to solve equations of this kind. But for purposes of the present time, it's fair to say that this is a differential equation and it describes some kind of behavior. Now that behavior could be of a mass m that is attached to a spring and fixated with a wall. And lying on the floor, and the floor is frictionless, so there is no friction between this mass and the floor. So this physical system, which we can observe in the laboratory or in our daily lives, is modeled through an equation. So if we solve this equation, we can predict what the behavior of this system will look like. Likewise, if I draw another system which looks like a resistor with an inductor, a switch, and some kind of battery. Now this is also a physical system that we come across or encounter in our daily lives or in the laboratory. This system can also be explained by an equation or by a model, and this is a relevant model to explain this system. So apparently two different systems, different looking systems which belong to different realms. This you would study in electromagnetism or circuit theory. This you would study in mechanics conventionally. But both of these systems can be described by a common language, and that is called the model. We have light. Light permeates this room. Light is everywhere in the universe. Now light comprises an electric field. So this is an electric field E, which is changing with time. So this is the time axis, and you have an electric field that is going up, down, up, down, up, down, like a sinusoid. And you also have a magnetic field which is normal to the electric field. Electric field is a vector, remember, and so is magnetic field. So this is called an electromagnetic wave or light. An oscillating electric field and an oscillating magnetic field, both of them are perpendicular to one another, and it's changing with time. So this physical phenomenon or this physical entity is also described by a model very similar to the differential equation that I've written. So apparently different looking phenomena, different looking processes can be described by common models. Now, one of the most common models that is used in physics is called the model of the harmonic oscillator. So harmonic oscillators are everywhere in the universe. From light to masses attached to springs to electrical circuits to string theory. Most of the objects that we see around us, most of the physical processes, they can be modeled like harmonic oscillators. So if you understand harmonic oscillators and how they work, how they are modeled, I think you've understood almost half of physics. Half of all of physics. So let's focus on a harmonic oscillator and let's see what the energy of a harmonic oscillator is. And from that we'll introduce the concept of internal energy. Suppose we have a mass attached to a spring. Now this is described by a certain law called the Hooke's law. Does anyone remember what the Hooke's law is? What is it? Bataiye? The force is proportional to the extension. So if I have a spring like this and I attach some weight to it, I'm applying a force. The force is being applied by the earth through gravity and this spring extends. There is an extension. Likewise, I can apply a force in the opposite direction, making this spring to compress. Larger the force, larger will be the extension or the compression. And this is Hooke's law. This is something we normally encounter. And the force is directly proportional to the extension, and the relationship is defined through a proportionality constant K, the spring constant, and there's also a minus sign prepended with it. Alright. Now if I have this spring, this is its normal length. If I extend it, then its energy must increase or decrease. Suppose I extend this spring and keep it there. Will its energy have gone up? Now the spring is at rest. The spring is still at rest, but it is extended from its normal position. Would this spring store some kind of energy in it? Yes. What kind of energy? Elastic energy. It's called elastic energy, but it's a kind of potential energy. Because there's no kinetic motion, the spring is at rest, but it has extended. So there is a kind of potential energy which you correctly referred to as elastic energy, which is just nomenclature. So there is some potential energy associated with this extended spring. Likewise, if I compress it, there is again potential energy associated with it, even though the spring is still at rest. Now this energy is a form of potential energy. It's denoted as U. Now is there some relationship between the U and F? Something that you learned probably from your mechanics class? Okay, last row. Can you point out some relationship between F and U? The very last row. क्या? बोले? जी? F equals? Mu R. What is mu? There is no friction here. आप बताएं? But what's the relationship between F and U? F is directly proportional to U. आप बताएं, आपने हाथ खड़ा किया पीछे? Right? So, I'm sure you've come across this relationship. Sorry, it's U. I'm sure you come across this relationship. Correct? Now given F, can you find what the potential energy associated with this compressed or extended spring would be? How would you find U given F? You will integrate F. And what's the result? U would turn out to be? अब जरा करके दिखाएं मुझे. करो. आगे करो ना. F क्या है? फोर्स तो है लेकिन है क्या F? ये F. दिखाएं आप. आगे आपने इंटीग्रेशन तो पढ़ी हुई है ना. ये पता चल. Actually, this is quite strange. So U is given by minus the integral of f dx. It's very simple. F is given by half kx. Is that it? Is that it? Plus some constant. Now this is one of the simplest questions I would ask. It's an example of a very simple question. Now given this Hooke's law, given the force, I can calculate what the potential energy associated with a compressed spring or an extended spring would be like. Now could you please plot, is this U a function of x? Yes, it is. Can you please plot U as a function of x? Ignore this C for the time being. पहले जो मैंने कहा वो करो. जी कहां से आया? So this negative sign comes from here and then F is negative, so both of these negatives cancel out. Could you please plot U versus X? प्लॉट करके दिखाओ. एक्सिस लेवल करें. एक्स नेगेटिव भी हो सकता है. X can be positive or negative. Is K positive? K is positive. So if I ignore C, I make two axes. I have X here, always label your axes, and I have U here, the function of X. So this is a plot of the potential energy versus X. At X equals 0, the potential energy is 0. And X equals 0 means the normal, the breathing state of the spring, where it just sits on its own. And you extend the spring, the potential energy goes up. Alright? You compress the spring, the potential energy goes up again. What kind of shape is this called? It's called a parabola. So if X goes to infinity, the potential energy goes to infinity as well. Now, how do I modify this graph if I would like to include the effect of C? ऊपर ले जाएं, नीचे ले जाएं, ठीक है? It doesn't matter. And why am I justified in including a C? Because it's an indefinite integral. What's the physical reason for it? It may already have been stretched.
It may be under the influence of gravity.
Under the influence of gravity, okay. C denotes an initial potential energy. It could be inside the Earth's gravitational field. So C is just an arbitrary constant. Mathematically, C does not matter, because if you take the derivative of this, you would still get minus kx. 1. Number 2, potential energy is defined with respect to some reference. So we as human beings have the liberty of choosing that reference. We can choose whatever reference we like. So we can add any C to our pleasure. It doesn't really matter. So we can shift this curve down. We can shift this curve up by C. It doesn't matter. So this is the curve of an ideal harmonic oscillator. It's an ideal harmonic oscillator. Of course, no oscillator is always ideal. For example, if I take this spring, I extend it, I remove the force, it's going to come back to its breathing state. Now if I extend this spring by a larger amount, still it will come back to its breathing space. But if I extend this, keep on applying a force like this, there's going to be a point where it's not going to come back to its original state, which means it has lost its elasticity. It's no longer a harmonic oscillator. So there is a limit to this graph. Beyond a certain point, I keep on applying a force, the X will not increase. So there is a limit to the harmonic oscillator, and it will deviate from ideality if the force is very large. If I compress this spring, right, such that the coils are now perfectly touching one another. It's a very stiff spring. It has a large spring constant K. I cannot compress it. But if it were a slinky spring, I would compress it such. I keep on applying force. It will not compress any further. So there are deviations from ideality. Nothing is ideal in physics in the real world. So we will have to modify this harmonic oscillator curve for non-ideal springs. But let me draw an example non-ideal curve. This is X, this is Ux, this is the ideal curve with an arbitrary value of C, and a real curve would be very close to ideal when X is small. It's very close to ideal when X is small, But when x becomes large, it deviates from ideality. Somehow, it deviates from ideality. So in this small region, in this small regime, I have a good approximation of an ideal harmonic oscillator when the displacement is small. But when the displacement is large, I get deviations from ideality. Likewise, if we consider a pendulum, which is also a harmonic oscillator, we can define, it's defined by the same model equation roughly, where k is now something different physically, but it's the same kind of equation. Now this pendulum is also a harmonic oscillator. It will behave as an ideal harmonic oscillator if the amplitude of oscillation is small. It's called the linear approximation, where it behaves like an ideal oscillator. If this amplitude of oscillation is large, it will deviate from ideality. So real systems are not ideal, but most systems that we encounter can be approximated by ideal harmonic oscillators under certain limits. Alright, one thing I would like to ask you here is this mass attached to the spring example. If I plot a graph, you see in this course we'll use 3 tools at the same time. We'll use language, English language mostly, because language is very important in conveying ideas of physics. The use of improper language can result in improper concepts. So we'll focus a lot on language, especially important for quantum mechanics, जहाँ particles, waves, energy, yes, heat, ये सब बातें हो रही हैं. तो it's very important to focus on the proper language. एक बात हम करेंगे, लैंग्वेज इस्तेमाल करेंगे. दूसरा, हम डायग्राम्स और ग्राफ्स बहुत ज़्यादा इस्तेमाल करेंगे. और तीसरी चीज़ जाहिर है इक्वेशंस. For some people this is the most dreaded part, but for some it's the most pleasing part. Anyways, if I would like to make a diagram or a graph of time versus the potential energy, U as a function of time, I have extended the spring and let it go. Could you please on your notebooks draw what the potential energy curve will look like? I extend the spring and let it go. When I ask a question, aap kare.
Why, when x is decreasing, why does the potential keep going up?
Equation se nazar aa raha hai. Because you're compressing it, it still has energy stored in it. You let it go, it can do work.
So we can, but in the non-ideal one, so
it could go any way. That was just an example for departure from ideality. ठीक है? Kindly plot the potential energy versus time. It's ideal, there's no friction. First question, does the potential energy remain constant with time? No, it doesn't, because the extension is changing all the time. कम क्यों हो रहा है? There's no damping, there's no friction. शाबाश. There's no damping, there's no such thing as decay. शाबाश, that's good. ये एम्पलीट्यूड कम क्यों हो रहा है इसका? डैम्पिंग नहीं हो रही.
You're going to increase it and then you're going to let it go?
You're going to extend it and then let it go.
मतलब कंटिन्यूस बनाते रहे हम.
हाँ. There's no energy wastage here because There's no friction we are assuming. Now these are very simple concepts from physics that you must have learned in your A levels or mechanics. Even a student who studies law in this university but has taken physics up to 12th grade can take this course. But you must have studied some physics, or otherwise you shouldn't be in the university or in SSE or in this class. But if you studied up to grade 12 and you have clear concept, these are very simple questions I'm asking. First, remember I'm looking at the potential energy versus time. And there's no damping. So the potential energy oscillates, we know that. It's extended to the maximum, it's maximum. Then it goes back to its normal position, it's zero. It goes the other direction, it goes up again. Right? So the potential energy has to go up and down. At the normal position, it's zero. Can the potential energy go negative? No, it cannot. So the curve will look like this. These are the equilibrium positions. So when this goes to zero, the spring is at x naught. The spring is at x naught here. The spring is at x naught here. When it's at the maximum, and x naught is the equilibrium position. When it's maximum extended to the maximum, the value of x is x naught plus the amplitude. Here the value is x naught minus the amplitude. Again it's x naught plus the amplitude, and so on. So here we have the normal position of the spring. Baatein na karein. Here we have the maximum extension of the spring. Here we have the normal position again, and here we have the maximum compression. Both the maximum extension and the maximum compression have the same value of the potential energy, the maximum. So this is a plot of the potential energy versus time. Can you plot the kinetic energy versus time? Sorry?
Why doesn't the potential energy go negative? Like if it's compressed,
The potential energy can't go negative. There's no concept of negative potential energies. It's preferable if you drew the kinetic energy curve on the same graph. This is good. Remember, I draw a special shape here. It's not a sine or a cosine. It's slightly different from a sine or a cosine. Shabash. Good. Sine or cosine आपने बना दी, slightly different.
Why wouldn't the potential energy decrease like that in a fluid in such a way? Why is there a curve like that? हमें किस तरह पता चलेगा कि वो decrease हो रही है वो?
मैं आपको बताता हूँ. That's fine. That's good.
X naught पे हम लोगों ने zero ले रहे हैं, but because of these two first when we stretch the spring, shouldn't it go beyond the equilibrium position?
It goes the other way, yes. It does. So one lobe corresponds to going to the right, and the next one corresponds to going to the left.
So it's a ये वाली चीज़.
How is there potential energy in the spring when it's not stretched initially when time is zero? how is there potential energy?
Because we have stretched it and we let it go at its maximum amplitude.
Started this graph once it's been let go.
Right. All right, so there are different ways of approaching this question that I've asked. The potential energy goes up and down, up and down. The kinetic energy also goes up and down. When the potential energy is zero, that's at the rest position, the kinetic energy is maximum. When you reach a turning point, the maximum amplitude point, either extension or compression, the mass momentarily comes to rest. So the kinetic energy goes to zero. So I can draw a similar curve, but which is displaced with respect to the potential energy curve. Right? So this pink curve is for the kinetic energy versus time. Can you tell me something about the conservation of energy here? Energy is being conserved. The sum of the kinetic and the potential energies is zero, is constant. So I can draw a straight line corresponding to the total energy, and that straight line will lie here. Sorry, at the tips. So energy is being conserved in this system. So there is a tug of war between kinetic and potential energies, or a constant interchange of energy, but the total energy remains constant. So I can approach this problem mathematically as well. If I solve that equation, which you will learn in your recitations, I will find out that x as a function of time is some amplitude a, for simplicity cosine some frequency omega t, and the potential energy is half kx squared. It's half k a squared cosine squared omega t. So this yellow curve is a graph of a cosine squared function. The kinetic energy as a function of time is given by half mv squared. Now m is dx by dt, right? So can you tell me what the kinetic energy will be? Can you calculate what the kinetic energy is going to be? Yes, you can. You have x. It turns out that the kinetic energy would be half m dx by dt is given by minus omega a sine omega t squared. Half m omega squared a squared sine squared omega t. And you will find out that this m omega squared is equal to k half k a squared sine squared omega t. So you have a sine squared function for the kinetic energy, and the sum of these functions, the potential and the kinetic energy, is going to be constant, half ka squared. So higher the amplitude, higher the energy. यहाँ तक बात समझ आई? Now let me draw the harmonic oscillator potential energy curve again. Now this parabolic trough represents the potential energy. Now the energy of the system is constant, and we are free to choose where this curve starts from. We are free to displace it in any direction. But let's, for simplicity, in this case, let's draw the parabolic curve such that you start at 0 to make things simple. This is x, this is 0, and this is a curve of ux. अब देखो amplitude a है. See, so you can put an a here and a minus a here. It's very important to understand this because this will form the basis of our quantization discussion next week. So this is a minus a here. X is vacillating, it's changing between plus a and minus a, plus a minus a. Okay? So the potential energy is going up, back down, up, back down. So it's like a marble that is placed in this trough. The marble is going up, down, up, down, up, down, right? So the potential energy is going up, you reach A, the potential energy goes back down, then it goes up in the opposite direction, reaches here, and goes back down, right? And the kinetic energy changes in an analogous fashion, such that the total energy remains constant. At this point, what's the nature of the energy? Is it kinetic or potential? It's totally potential. Here, it's totally potential energy. So the total energy is also equal to the potential energy. Here, the total energy is equal to the potential energy. And what's the total energy here going to be? It's going to be kinetic energy, but its value is going to be the potential energy here. So I can draw a straight line connecting these points, and this straight line is a graph of the total energy, which is the sum of U and K. Okay? So the potential energy is constantly changing, but E is fixed at this value of the energy. ठीक है? और यहाँ पर सब की सब ये जो सारी एनर्जी है, the difference between the total and the potential energy is wholly kinetic. Here it's a mixture of the two. So here at this particular value of x, there is some potential energy, U at this value of x, and there is some kinetic energy. Now on this graph, let me just please a minute. On this graph, the same graph, can you draw what the kinetic energy with respect to x will look like? बना के दिखाओ. Shabash. Plot the kinetic energy on this same graph. Shabash, that's good. It's fine. बिल्कुल ठीक. It's going to be an inverted parabola, such that the sum of the blue line and the pink line remains this constant green line. Now let's start talking about atoms. Now we have a description of a harmonic oscillator. We know what the energy functions look like. Let's talk about two atoms in close proximity. देखो हम इस कोर्स में मैकेनिकल सिस्टम से मॉडल से कितनी जल्दी इजीली एटॉमिक डिस्क्रिप्शन पे आ जाएंगे. दिस इज व्हाट आई कॉल द एटॉमिस्टिक व्यू ऑफ हीट एंड एनर्जी एंड थर्मोडायनामिक्स. नाउ सपोज वी हैव टू एटम्स. दिस इज अ पॉजिटिव न्यूक्लियस surrounded by an electron cloud, and the two atoms are very far apart. right? So there is no interaction between these atoms. They live in their own worlds. They're so far apart. But these are really neutral atoms. Now let's fix our reference for energy. When the two atoms are brought close together, one would expect some kind of interactions, because these, although they are neutral particles, but there is a positive nucleus and a negative electron cloud, a positive nucleus and a negative electron cloud. So this nucleus has to interact with this electron cloud electrostatically. Now suppose these atoms are brought close together, their potential energy is going to change, right? It's just like if that wall is a positively charged wall and I'm negatively charged, and I would like to move closer to the wall, my potential energy is going to change. It's going to in fact decrease because that wall is pulling me towards it. And if I move further away, I'm going against the electrostatic interaction, so my potential energy is going up. It's just like having some mass and moving it away against the force of gravity. So these neutral particles will interact, even though they're neutral, they will interact through electrostatic interactions. Now if I move this particle closer, the potential energy is going to change. We know that. Now I gradually move this neutral atom closer and closer to the other neutral atom. What happens really is that this positively charged nucleus is going to attract the electron cloud. I'm giving a very simplistic description. Is going to attract the electron cloud towards it. So this sphere of electron cloud will slightly change its shape. It will bulge towards the positive nucleus slightly, and there is a constant tussle between this electron cloud and this electron cloud, because this electron cloud wants to repel. Anyways, this shape is distorted slightly, and this potential energy will eventually change. So if there is more negative charge facing this atom, there is a force of attraction between this positive nucleus and this negative charge. So the potential energy is going to decrease. When the atoms were very far apart, the potential energy we assume to be zero. That's our reference. Now we would like to plot a graph between the distance between the nuclei R, between the atoms R, and potential energy U, which is now a function of R. Now when the atoms are very far apart, what's the potential energy? U is zero. So somewhere far apart you're at zero. This is zero. Now you bring the atoms close together, they would like to attract one another through electrostatic attraction. So it's just like moving a positive charge close to a negative charge. So the potential energy is going to decrease. Right. Now it will reach a certain point, and then what's going to happen is the nuclei, they will start repelling each other. So you cannot push the atoms further together. The only way you can do that is by increasing its potential energy. So the potential energy takes a twist here and it starts going up. So this region, this point where the potential energy is minimum, is, let's denote it by R naught. If these were two hydrogen atoms coming close to one another, for example on the surface of the sun, if they were coming close to one another at a particular value of R naught, that's a stable configuration because it has the minimum potential energy. They would like to form a bond. In chemistry you generally call this the bond length. They will form a bond, but if you try somehow to push these atoms further together, as happens in a fusion experiment, you try to push these atoms further together, the potential energy goes up. So this is just like a spring mass system. You are compressing the spring, the potential energy is going up. You are extending the spring, the potential energy is going up. So this is somewhat similar to a harmonic oscillator with some notable differences. This region is the region of preferred attraction, and this is the region of preferred repulsion. Now, the harmonic oscillator potential energy curve is totally symmetric. This is not symmetric, this is asymmetric, because it tapers off to 0 for long r's and goes to infinity at small r's. But in this region, it approximates a harmonic oscillator. It approximates an ideal harmonic oscillator when R is very close to R0. So in this region, say, when R is within this range, that is R minus R0 is smaller than some number epsilon, where this number is epsilon. When R is very close to R0, you close to the equilibrium position, you can approximate the interaction between these two atoms like a harmonic oscillator. Right? So if you have a, let me finish, sorry. If you have a chlorine molecule, it's a diatomic molecule, two chlorine atoms, they are bonded together. The general bond representation is like this. So at this particular value of R0, which is called the bond length, you can model this chlorine molecule, this diatomic chlorine molecule, as two chlorine atoms which have a certain mass associated with them, and they are connected with the spring. This is a perfectly legitimate equivalent model for this chlorine molecule, because this has the potential energy curve of a harmonic oscillator, and our atoms which are interacting also are described by the same model. So atoms inside solids, inside gases, inside molecules, when they are bonded with one another, they can describe in terms of the harmonic oscillator. Now we've talked about graphs, we've talked about the equivalence with the harmonic oscillator, but there should also be an equation that describes this potential. For the ideal case, we have half k x squared. We must have something here. It cannot be half k r squared, because that will go to infinity. So the potential energy for this curve is generally given in this form: UR equals E, some E naught, 1 minus e raised to power minus alpha r minus r naught squared minus E naught. Where this energy is E naught. And this is called the, please, just a minute. This is called the Morse potential. Now what I would like you to verify is, look at this potential energy equation and verify that for very large r, the potential energy, does it really go to 0? If I put R goes to infinity, will this potential energy, what will it approach? 0, because this is going to be minus infinity, this is 0, and E naught minus E naught is going to be 0. What is the value of this potential at R equals R naught? So this term goes to 1, because R minus R naught is 0, E raised to power 0 is 1, 1 minus 1 is 0, this term disappears, you get minus E naught. Right? So at R naught the value of the potential energy is minus E naught. केमिस्ट्री में इसको बॉन्ड एनर्जी कहते हैं, इस एनर्जी को पढ़ेंगे, बॉन्ड एनर्जी, ठीक है. और R जब 0 को अप्रोच करेगा, when R is very small, what happens? When R minus R naught goes negative, then this term blows up, it becomes very large, and so does the potential energy. So this potential describes two atoms that are close to one another. It also describes quarks inside a nucleus. It describes a large number of various things in physics. ठीक है? So अभी हमने ये देखा कि जो potential energy harmonic oscillator का concept था for mechanical systems, it automatically carries over to the description of interactions between atoms. All right. G.
Morse potential, does it refer to the equation or is it a specific point?
The Morse potential is the potential that satisfies this kind of equation. अच्छा, आप में से जो मैथमेटिकली इंक्लाइंड हैं, मैं उनसे एक सवाल पूछूं. This is a some constant. Alpha is some positive constant. If I change the value of alpha, what will happen to the shape of this curve? Will it change these critical points? No, it will just change the width of this. The width of this depression. So changing alpha will change the width of this depression, and you can verify this in MATLAB or any other software of your choice. All right. So there were a couple of questions. हाथ खड़ा करें. There were a couple of questions. Yeah, have I answered those questions? All right. So let's talk about internal energy. And let's proceed slowly to the first law of thermodynamics. चलें, खामोश हो जाएं. अब देखें, suppose we have a solid, right? We would like to model a solid using harmonic oscillators. We have a crystal. Now I can draw a simple view graph that can attempt at modeling the behavior of a crystal. For example, I have an iron crystal. An iron crystal. So I can model this crystal by atoms of iron. Each of these circles represents an iron atom. So I can model this iron crystal as a network, three-dimensional network of iron atoms, and they're connected by springs. Each atom is bonded to a neighboring atom. It has some environment. It's being bonded to neighboring atoms, and those interactions are described by the Morse kind of potential. They're described by harmonic oscillators. So any solid that I talk about, any material that I talk about is comprised of atoms, we know, and there is certain interaction between these atoms, there's certain bonding between the atoms. So we have a large network of harmonic oscillators inside the solid. So this is how we're going to model a solid in general terms. So everything that we've learnt about harmonic oscillators should also apply to solids. And in fact, this is how Einstein was originally thinking about the specific heat capacity of solids. He was modeling his solids with networks of harmonic oscillators. This is how quantum mechanics was given born to. You model your atoms and their excitations by harmonic oscillators. So it's a very valid model. So what we've learned about harmonic oscillators directly applies to materials in our real world. Now what we are interested in is the concept of internal energy. Alright, so let me introduce what internal energy really means. Suppose I have a diatomic molecule modeled by a harmonic oscillator, two atoms that are bound together, and this molecule as a whole is moving with a velocity, with a speed v. Now take another example. I have the same molecule and now it's compressed. And the molecule is now moving with a velocity, the same velocity v. Third example, the same molecule but the harmonic oscillator is now extended, and this molecule is now moving with the same velocity v as a whole. So we have a spring, like this is our molecule. We have this spring, this is natural length. We've changed the length, by the way. So this is our new natural length of the molecule, and it's moving with a velocity v. The molecule is translating. Now I compress this spring, right? Very difficult to compress it, but I compress this spring, and now the same molecule is moving with a velocity v. And now I extend the spring, right? The distance between the atoms has gone up. Now the same extended spring is moving with a velocity v. Now what's the difference in the energies between the three systems? What about the kinetic energy of the molecule? It's the same. So half capital M is the mass of this molecule, v squared is the kinetic energy of this molecule. And this molecule will have a center of mass. This is the velocity with which the center of mass moves. Correct? आपने center of mass पढ़ा होगा ना? This is the velocity with which the center of mass moves. So this is the kinetic energy associated with the center of mass motion of the molecule. And all three cases will have the same kinetic energy associated with the center of the mass. However, in all three cases, the molecule has some additional energy which we've already referred to as U. And that energy, which is internal to the molecule, is called the internal energy. So these two cases will have a higher internal energy than the first case, because we have compressed the spring and we have extended the spring here, even though the center of mass kinetic energy is the same. So the total energy of these molecules, each one of them, will be equal to kcm, the center of mass kinetic energy, plus some internal energy which we generally denote by U. And I will just put an internal sign here just to mention that this is internal energy. So the total energy is now a sum of the kinetic the center of mass kinetic energy, and the internal energy. So the internal energy is the energy which is calculated within the reference frame of the object. It's within the reference frame of the object. Suppose I were a microscopic being, very small object, smaller than a chlorine atom, and I was sitting inside the chlorine atom. And the velocity, this is uniform velocity. I will not have noticed that the molecule is moving. But I would have noticed that I'm being compressed or extended. So this energy, which is internal to the molecule, the name says it all, which is internal to the molecule is called the internal energy. And the total energy, in the lab frame, in our cozy classroom, we observe that the system has internal energy and it has kinetic energy as a whole, because we are at rest with respect to this moving object. So the energy that is associated, that is measured inside the frame of reference of the object or the molecule or the atom is called kinetic energy, or is called internal energy, sorry. ठीक है, it's a very subtle concept. तो इसको अच्छी तरह ज़हन नशीन कर लें. All right. Which part?
Last part.
The definition. All right. So the internal energy is the energy that is measured inside. Remember this word, inside the frame of reference of the object itself. And the object could be an atom, it could be a molecule, etc. itself. So even though we have different center of mass kinetic energies, or the same center of mass kinetic energies, the internal energies in the three cases will be different. So now you have a solid that I drew over there. There are a large number of harmonic oscillators. Correct? अब इस बात को ध्यान से सुनें. Let's move to the solid, example of the solid. Associated with this harmonic oscillator, there is a kinetic energy and a potential energy. Associated with this oscillator, there is a kinetic energy and the potential energy. And the solid as a whole could be moving as well. So there is energy that is internal to this solid, and there could be center of mass motion as well. Now if we have a molecule that is translating, which is it's locomoting, it's changing its position, the kinetic energy associated with this, there's an energy associated with this translation. Okay? That is called the translational energy. The translational energy. You compress the spring or extend it, there is some energy associated with this compression and extension. That's called a vibrational energy. Right? So this translational energy is kinetic, this is potential. We could also have a scenario in which the molecule is in fact undergoing a different kind of motion. That is, if we take a center of an axis of rotation here, the molecule could be rotating about this axis of rotation. So it could be undergoing rotational motion as well. So there's a kinetic energy associated with this rotation as well. So let's call this the rotational kinetic energy. Now the total energy of a system. Right, okay. And there's another kind of energy as well. say, I don't know if it's proper to introduce this concept here, but let me talk about the energy of being. Any object that has mass, whether it's at rest or moving, it will have some energy just because it exists. This is Einstein's famous postulate, and this energy is given by mc squared. This is the energy of existence. I exist, therefore I am, which means I have some energy.
So why doesn't it apply to the photon?
This energy, the photon also has this energy, but it doesn't. Right, but this is not necessarily the rest mass. We'll learn about this. This is not the rest mass, this is the relativistic mass. So a photon does have momentum. It can exert pressure, radiation pressure on solar panels. So it does have this energy of being as well. That mass, yeah, you change the mass, its energy is going to change. If you change these energies, it's equivalent to saying that the mass is changing. Alright, but let's not talk about this for the time being. So the total energy of a system, E, will be given the internal energy of a system, right? We're talking about the internal energy of a system. Could represented by U or E, doesn't matter. I've written an internal to specify that this is the internal energy of a system. Now I'm not talking about the center of mass energy, only the internal energy. This internal energy can have different categories or components, right? It could have energies due to the translation of our harmonic oscillators. The harmonic oscillators inside the solid can be translating. For example, if you have a container of gas, the gas molecules are not static, they are translating with certain speeds. So there could be translational motion associated with the constituents, okay? And this adds to the internal energy of the solid or the material or the gas, okay? देखो एक गैस का एक सिलेंडर है, there's a piston, and there are gas molecules inside this cylinder. Right? So these molecules are translating. The cylinder is static. It's not, the piston is not moving, it remains where it is. But yet the constituents of this gas, they are translating. So they must possess translational energy. I have to finish here, so let me finish please. So there is translational energy, and that is contributing to the internal energy. Then we can have vibrational energy. That is, the oscillators can vibrate. This mode can exist. We can have rotational energy. The molecules can rotate about certain axes. And then we can have other forms of energy as well. Remember, this vibrational energy is kinetic as well as potential. This is kinetic, this is kinetic. But it's all internal to the system. The system as a whole is not moving, it remains where it is. So all of these contribute to the internal energy. And there can be other categories of energy as well. Plus, for example, chemical energy. Photosynthesis. Sunlight falls on chlorophyll. Energy is stored in the ATP molecule. There is no kinetic energy or rotational or translational vibrational energy. Yet energy is being stored inside the plant. Inside the ATP molecule, the molecular rotors and the motors can move with the help of the energy derived from ATP. So that is also contributing to the internal energy. देखो प्लीज सिर्फ 2 मिनट और सब्र कर लें. तो ये जो केमिकल एनर्जी है ये भी कंट्रीब्यूट कर रही है इंटरनल एनर्जी को. there could be magnetic energy, and there could be other forms of energy as well. So all of these contribute to the internal energy of the system. And if you look at these components, the random part of these components, is given a special name, and that is called thermal energy. So in the next lecture, I will talk about the random components of these energy contributions to the internal energy. Remember, this is not present in any textbook, so this is an idea that I would like to present here, which is the proper way of understanding what thermal energy is. And in the next lecture, I will focus on thermal energy. I will tell you that the word heat cannot be used as a noun. There's some problems with that. There is no such thing as heat inside a body. There's thermal energy inside a body. I would like to tell you what thermal energy really is and how that thermal energy contributes to the internal energy. See you next Tuesday.